Welcome to part 3 of our series of videos on simple machines. Now the first type of simple machine we're going to talk about in this video is a pulley. Now when you look at this pulley, this type of pulley that this person is using is called a single fixed pulley. The only advantage to using this pulley is you can change the direction of the force. So here this person's trying to pull the box up. Now the pulley's not mounted very high. I've often thought about having this type of pulley system in my garage mounted to the ceiling to store my bikes over winter. And would it have a good MA? Well, the MA would be 1, which means there really is no mechanical advantage. But here, the advantage for me would simply be I won't have to get up onto a ladder, I won't have to pick my bike up, and I won't have to hang it from hooks that I have up on the ceiling of my garage. Now, a pulley changes the direction or location of the effort force. And you saw that in a single fixed pulley. Or it may also be used to reduce the effort necessary to move an object. So here's 2 different types of pulleys. So let's talk about the MA of a pulley. Now, finding the MA of a pulley is really easy. Now, the number of supporting strings or the total number of ropes minus 1. So if I look at pulley number 1 here, it says the MA is 1. How do I calculate that? Well, what I do is I look at both these strings right here. Okay, so I can take the total number of ropes minus 1. Now you might be saying, well, Mr. Ratoon, this rope goes around here, so it's all one piece of rope. What do you mean? Well, you're going to have to imagine this is 1, this is 2. When I look at the one over here, it's 1, it's 2, it's 3. So again, you're right, it is all technically one rope, but you don't count it that way. You count these strands right here. So it's the total number of ropes, so here there's 3 minus 1. So this is why this one has an MA of 1. This is why this one has an MA of 2. And we'll talk about the one instance where counting this does not work. Or what you can do is you can look at the total number of supporting strands or strings. So if this is the one that you're pulling on, you just count the other 2. So it's 2. Or if this is the one that's being pulled down by this counterweight, well then, or if it's this side, it doesn't matter what side it is, well then it's only 1. So I always like to count the total number of ropes and subtract 1. So a single fixed pulley only changes the direction of the force. And you saw that right here, a single fixed pulley. And the reason why, and there's just one pulley. Here there's 2. So why does a single fixed pulley it's only useful for changing the direction of the force? Well, that's because the MA is 1. It's got no mechanical advantage. Okay, it has a mechanical advantage of 1, which means it's not increasing the amount of effort. It's not making work seem easier. So it's really just used to change the direction of force. Now the MA of a single movable pulley is simply 2. And I'm going to show you what that would look like. So here's a single fixed pulley. It's got an MA of 1. But here on the right hand side you see a movable pulley. So if you counted both these ropes and you said, well, there's 2 and 2 minus 1 is 1. This is the only one where the equation does not work. It's if it's a single movable pulley. So if we back up, here's a fixed pulley and here's a movable pulley, but the 2 are together. So it's not automatically an MA of 2, although this one has an MA of 2. But if we were to go here and say, well, look, this should only have an MA of 1 because this one is 1, this is 2, and 2 minus 1 is 1. And this is the only time it doesn't work. So if it's a single movable pulley, the MA is going to be 2. The next type of simple machine we're going to talk about is a wheel and axle. And you can see, well, there's several wheel and axles on here. There's the 2 larger wheels on the right-hand side, but if you look up near the guy's hands, those are also wheel and axles, smaller ones anyway. So a wheel and axle is a lever that rotates in a circle around a center point or a fulcrum. So the larger wheel or outside rotates around the smaller wheel, the axle. So again, typically the larger of the 2 is called the wheel and the smaller shaft is called the axle. Now you might look at this and say, fulcrum, is this a lever? What kind of is a lever? But yet here the lever is in the center and then the wheels around the outside of it. So it is similar to a lever in a sense that it does have a fulcrum. It's just kind of like the levers wrapped around the fulcrum instead of being on either side and having the resistance and the load. Or the resistance is the load or the effort. So bicycle wheels, and gears are all examples of a wheel and axle. Wheels can also have a solid shaft. So when I look at this screwdriver off to the right here, it's got a solid shaft with a center core as the axle, such as this screwdriver. A drill bit could be considered a wheel and axle. You don't usually think about it, and it's actually, well, when we look at the screwdriver, it could be considered a compound machine because it also has the wedge on the end as well. So even the log in a log rolling contest would be considered a wheel and axle. So here we see a wheel and axle. So how do we find the MA of a wheel and axle? Well, it's the ratio of the radius of the wheel to the radius of the axle, and it gives us the mechanical advantage. So we just have to look at the ratio of the two. What's the ratio of the wheel to the radius of the axle? And this will give us the MA. Now, typically we want MAs greater than 1, because what that means is we have to apply less force, but the trade-off is often distance. However, every once in a while, especially with wheel and axles, we actually want it the other way. So for example, if you were trying to gear something down that was going really fast and you want to slow it down, and you would use gears to do that, sometimes you would actually have an MA of less than 1. So it is possible that the larger thing could be considered the axle and the smaller one could be considered the wheel. It just depends on your circumstance. So again, how do we find the MA? It's the ratio of the radius of the wheel to the radius of the axle, and it gives you that mechanical advantage. So here we go. MA for the wheel and axle, it's the radius of the wheel divided by the radius of the axle. So here we see a couple more examples of wheel and axles. Now the radius of the wheel will be larger because one always, or again, almost always wants the MA to be a positive number. Now the last thing we're going to talk about, well, I'm not sure if it's actually the last thing or not. I've lost track of how many we've talked about. But here's the wedge. Now if you look at the wedge that the guy's using, does the top of it kind of look like an inclined plane and the bottom look like another inclined plane? If you notice that, you're actually correct. A wedge is simply an inclined plane which moves. And most wedges, but not all of them, are actually a combination of two inclined planes. A knife, as it cuts through, say, cheese or bread, would be considered a wedge. It's two inclined planes. An axe, a razor blade. Teeth are all good examples of wedges. Here you see the water. It's not cutting through solids, but it's actually cutting through the water. Or the top of a rocket as it cuts through the atmosphere. All examples of wedges. Now, generally, it can be anything that splits, cuts, or divides another object, including air and water. So the fan blades could be considered a wedge because they're designed to cut through the air. A lot of times when we think of the wedge, we think of the top picture here. Splitting wood is where I typically will use a wedge outside, where I actually call it a wedge. And to find the MA of a wedge, it's simply the length divided by the height. So it's the length divided by the height. So you might say, well, wasn't that how we found the MA of an inclined plane? Well, bingo! That's because a wedge simply is an inclined plane which moves. So again, that's why the MA seems to be very, very similar. So here is the last one, the screw. And a screw, like a wedge, is simply another form of an inclined plane. You might ask how? Well, look at what you see here. A screw is an inclined plane that is wrapped around a cylinder to form a spiral. So if you look at a screw, if you look at these screws or the screw and a crescent wrench, it's basically an inclined plane that's wrapped around that center cylinder. So we probably view screws all the time. We just don't realize it. The crescent wrench right there, that's a screw. Now, how do you find? Okay, so we're going to give you a really easy way to find the MA of a screw. And simply, what we're going to ask you to do is look at it. If it's got more threads, it has a higher MA. If it has fewer threads, it has a lower MA. Now, you can actually look at the pitch, and you can see how much it goes up, and you can more accurately predict your MA. But we're going to keep it really simple here and for what we do in class. Simply, we'll give you two. You look at them. If it has more threads, higher MA. If it has fewer threads, it's got a lower MA. And that's all we're really asking for you to be able to do with the screw. More threads, higher MA. Fewer threads, lower MA. As always, make sure you ask if you have questions about anything in the video. And don't hesitate to ask for help if you need help finishing up your notes or if you don't understand parts of your notes.